Recording. So this week we are, where are we at? There we go. That's what I want. We are looking at kind of the next level. It's statistics, but it's a specialized branch of statistics. Actually, it's part of operations research, which is where we take the statistics we've gathered and we start applying them to real life situations, mostly business situations. And so the small part of operations research that we're looking at in this course and looking at tonight is called linear programming. Now, linear programming is actually a fairly large topic. We are not going to be able to do it a lot of justice here in an hour and 15 minutes. But we'll get through the basics of it. This is one of those topics. This course was taken from a 15-week course down to a 12-week course about a year and a half ago, for reasons that had to be done. Financial aid and other things were forcing it to happen. But linear programming is one of those topics that used to be spread out over 2 weeks that is now squeezed into one, which means it's going to be a struggle to understand all of it. Now, I'll say more of that towards the end of the recording here. On what I mean by that. But let's go ahead and look at the basics here of linear programming. First of all, let's talk about graphing and inequality. If I have an inequality like 3x plus 5y is less than or equal to 15. Now, to graph that, we go through three steps actually. Step one is we graph the related equation. So for this, that would just be 3x plus 5y equals 15. When we do that, kind of a step two is we have to decide, is it a solid line or a dashed line? Well, a dashed line would be if it was strictly less than or strictly greater than. Solid line is less than or equal to or greater than or equal to. Less than or equal to means the boundary can be part of the solution. Strictly less than, the boundary is not part of the solution. It's not less than itself. So this is going to be a solid line because it was less than or equal to. And for the most part, all the inequalities we use in linear programming are less than or equal to or greater than or equal to. So it is a solid line. So let's graph that line, that related equation. Now there's a lot of ways we could graph this linear equation. We could turn it into y equals mx plus b form. I'm just going to use intercepts. 15 minus 3 gives me 5 for the x-intercept, so that's right there. 15 divided by 5 gives me 3 for the y-intercept. So my line goes through those 2 points. Now we need to decide which side of the line the solutions are on. Let's straighten that line out a little bit. Less than or equal to, it implies it's going to be below the line, but let's test just to be sure. I'm going to take a test point, and usually I use the origin, 0, 0. If I put 0, 0 in there, 3 times 0 plus 5 times 0, well, that's just 0. And that is less than or equal to 15. So that's true. So the solution is here. Now, many textbooks would have you shade this side of the graph saying that's where the solution is. But in linear programming, we want to block out parts where the solution cannot be. We're trying to restrict where the solution is. So what we're going to do is this. We're going to shade in this side of the graph saying the solution is not over there. We cannot go over there. So that's meaning the solution is telling us the solution is over here in this region. So that is step 2 and 3. Well, step 2 is the solid or whatever dash line. And then step 2 is shade the region. Again, we're not, some textbooks say shade the solution region. We're doing it the opposite. We're shading the part that is not the solution. So we're blocking it out so it cannot be used. Well, a system of inequalities then uses two inequalities. Let's take, for example, 2x minus y is greater than or equal to 9. And x minus 2y is greater than 3 or equal to 3. So let's see here. We have, for the top equation, 9 divided by 2x would be 4.5. So that's right here. 9 divided by -1 would be -9. So that's right here. So it's greater than or equal to, so it's going to be a solid line. Looks like that. If I chose the test point 0, 0, 2 times 0 minus 0 is not greater than or equal to 9. So that test point is not true. So that means we are, I'm just pausing because you think greater than or equal to, it should be above the line. Just making sure I didn't do something wrong. But nope, that is true. We're not shading above the line. So that is no solution up here. So I'm going to shade this in saying the solution is not on this side. So then we'll graph the other equation, this one here. 3 divided by 1 means 3 is our x-intercept. 3 divided by -2 would be a -1.5 would be our y-intercept. We draw that line across there. Let's see here. That one is going to, if we shade 0, 0 for our test point, 0 minus 2 times 0 is 0. Again, that is also not greater than or equal to 3. So we shade the top side of that line saying that is not the solution. So what our solution is here is, of course, these lines. And then this region here is the solution. So any point in that region would make that system of inequalities true. Well, what linear programming does is it takes it to the next step. We use inequalities called constraints to isolate a region of the graph. We call this region the feasible region. That's the region in which our solutions can occur. And then we have what's called an objective function. That we are trying to maximize or minimize. Depending on the problem. And now there's a lot of proof that's been put into this. We don't have time to go through the proof, but it's found that the maximum and minimum value of the objective functions occur at the corners of the feasible region. In other words, the intersection of constraints. So let's just jump into an example here of a linear programming problem. We are going to be asked to maximize. So this is our objective function because that's what we're being asked to maximize. P equals x plus 2y, subject to constraints. 3x plus 2y is less than or equal to 60. X plus 4y is less than or equal to 40. 2x plus 3y is less than or equal to 45. And now, of course, almost always implied, x is greater than or equal to 0 and y is greater than or equal to 0. We do have to write them to make sure, to verify that they are true, but that's almost always true in any problem. In real life, most values are positive. So now this is, since x is greater than 0 and y is greater than 0, we only have to look at the first quadrant of our graph. We can't be less than 0 for x and less than 0 for y. Now, I'm not going to shade that in because I'm going to be able to need to write stuff in the margin. So let's look at this top equation here, 3x plus 2y less than or equal to 60. 60 divided by x would be at 20. So this is the point 20 comma 0 is the x-intercept. 60 divided by 2 would be at 30. So this is 0 comma 30 up here. And we'll connect those with a line. And of course, we cannot be out here. We have to be less than that line. X plus 4 is less than or equal to 40. Well, 40 divided by 1 is 40. So this is 0, or 40 comma 0 out here. 40 divided by 4 is 10. So we're right here at 0 comma 10. Connect those with a line, and we have to be less than, so we can't be greater than. So we shade in the top side. We can't be up there. Let me do this. I'm going to switch colors here. So shade in the top side, we can't be up there. Let's do a different color for the next line. The 2x plus 3y, well, 45 divided by 2 is 22.5, so that's right here. So this is 22.5 comma 0. 45 divided by 3 is 15, so that'd be right here. This is 0 comma 15. And this line actually cuts across the corner here. I didn't draw it real straight, but it cuts across the corner of that graph. So we have a five-sided region here. We have 5 points that we have to consider. This point is 0, 10. This point here, of course, is 0, 0. And this point here is 20, 0. So those are 3 of the corners of our feasible region, of our intersection of constraints. We need to find these 2 points. Well, the first one is at the intersection of these 2 equations. So we have to solve that system of equations if we recall how to do that. 3x plus 2y, and the line's at equals 60, so we're just going to put in equals 60. X plus 4y equals 40. Now what I'm going to do here is I'm going to rewrite this top equation. I'm going to multiply it by a negative 2. What that gives us is negative 6x minus 4y equals negative 120. So that when we add those equations, 6 plus negative 6x, or x plus negative 6x is negative 5x. 4y and negative 4y is 0y. That cancels out, so the y is gone. Equals 40 plus 120 is, oops, that should be a negative 120, is negative 80. And we divide by 5, or divide by negative 5, I should say. X equals 16. Well, if x is 16, I need to find y. So I'll use this equation here, put in x. 16 plus 4y equals 40. I'll subtract 16. 4y equals 24, and divide by 4. Y equals 6. So that corner right here, this one is at 16, comma 6. Let's find the other one. That's the intersection of the other 2 lines, the x plus 4, y equals 40 again. And this one will be 2x plus 3y equals 45. I'm going to do something similar. I'm going to multiply this top equation by a negative 2 so that the x's are going to cancel out. So that'll be a negative 2x minus 8y equals negative 80. Now when I add them, 2x and negative 2x is 0x. That's canceled out. 3y and negative 8y is a negative 5y. 45 and negative 80 is a negative 35. So divide by negative 5 to get y equals 7. We have to plug that back into one of these equations. To find x, I'll put this one. So x plus 4y becomes 4 times 7 equals 40. Well, 4y is 28. So x plus 28 equals 40. We'll subtract the 28. X equals 12. So that point is at 12,7. So this here is 12,7. So our corners of our feasible region, which remember, that's where the maximum or minimum should be. We have 0, 10, 0, 0, 20, 0, 16, 6, and 12, 7. And remember, what we are testing is that objective function p equals x plus 2y, and we're trying to maximize it. So if I put in 0, 10, well, 0 for x plus 10 for y, so plus 2 times 10, that's just 20. Well, 0 plus 2 times 0 is just 0. 20 plus 2 times 0 is going to be 20. 16 plus 2 times 6, well, 2 times 6 is 12. 16 plus 12 is 28. And here we have 12 plus 2 times 7. 2 times 7 is 14. 12 plus 14 is 26. Our largest value there is right here. So we obtain a maximum value of p equals x plus 2y of 28 when x equals 16 and y equals 6. So my WebAssign is going to ask you for the values of x and y, the ordered pair. It's also going to ask you then for the maximum value or the minimum value of the objective function, depending on whether you're maximizing or minimizing. Well, what we did here was a 2-variable problem. Because it was a 2-variable problem, we could graph it. Well, if it's a 3-variable problem, graphing it is not so easy. We can't really see the graph in 3 variables. An equation in 3 variables is a plane on a 3-dimensional graph. So we would have a 3-dimensional region and a lot of corners, at least 6 corners to deal with. Well, actually, we could get down as few as 4, but it's just not something that's feasible to do. Locating those corners without technology is really not feasible to do. So we look at algebraic methods of solving, just like we did with systems of equations. Way back in algebra, you started out by graphing them to see where the lines cross, but then we moved on to algebraic methods so that it would be simpler to solve. Let's do one more example using graphing just to get a word problem in here. We're going to, let's do this one. Let's say a calculator company makes scientific calculators and graphing calculators. So I'm just going to call them SCI and GRAF-PF for graph and scientific. There is a demand. Demand is at least, what is it, 100 scientific and 80 graphing each day. capacity, production capacity, is no more than 200 scientific and 170 graphing per day. So we cannot produce more than 200 scientific or 200 graphing calculators in a single day. A shipping contract exists for a minimum of 200 combined units per day. The company loses $2 on each scientific calculator and gains $5 on each graphing calculator. This is pretty common. A company will produce one product at a loss just to satisfy customers. If customers have to go to another company for one product, they tend to go to that company for all their products. So here, we're trying to maximize profits. So we're going to have an objective function. We're going to maximize our profit, which is going to be a -2. I'm going to let the scientific calculator be X and the graphing calculator be Y. So -2X plus 5Y. We lose $2 per scientific calculator, earn $5 per graphing calculator. Subject to the constraints, we have to have at least 100 graphing calculators, at least 100 scientific calculators, at least 80 graphing calculators. We can produce no more than 200 scientific calculators and no more than 170 graphing calculators. Now it's implied that X is greater than or equal to 0 and Y is greater than or equal to 0. So if we try to graph our feasible region here, I'm going to start out with my restrictions on X here. X has to be at least 100. So it can't be over here. And no more than 200. So it can't be over here. Then our restrictions on Y. Y has to be at least 80. Can't be less. And no more than 170. Can't be more. So we're in that rectangle is where we're restricted so far. So we didn't really need the X has to be greater than 0 and Y greater than 0. Now the one restriction we have not talked about yet is our shipping contract. X plus Y has to be at least 200 units a day. So we go to graph that. We'll go from 200 to 200. So that cuts across the corner here, and of course we can't be less than that, so that blacks out this part. So we have 5 corners of our feasible region here. 3 of them are pretty easy to find. This one here is just 200, 80. This one up here is 200, 170. This one here is 100, 170. This one here, we know that the X coordinate is 170. If I put 170 in here, or sorry, not 170, the X coordinate is 100, sorry. If I put 100 into this equation for X, Y would have to be 100 to make it equal 200. We know here the Y coordinate is 80. If I put 80 in here for y, x would have to be 120. So those are the corners, the vertices of our feasible region. So if I go around the horn, I have 200, 80, 200, 170, 100, 170, 100, 100, and 120, 80. And our objective function, we are trying to maximize p equals negative 2x plus 5y. So here we have negative 2 times 200 plus 5 times 80. Well, negative 2 times 200 is a negative 400. 5 times 80 is positive 400. I got an extra 0 there. I got to erase. That adds up to 0. This here would be negative 2 times 200, which is a negative 400, plus 5 times 170. Well, 5 times 170 is 850. That adds up to 450 units. That's their largest number so far. This one is negative 2 times 100 plus 5 times 170. Well, negative 2 times 100 is negative 200 plus 850, that's 650. This one is negative 2 times 100, which is negative 200, plus 5 times 100, which is 500, adds up to 300. And here we would have negative 2 times 120 plus 5 times 80. Negative 2 times 120 is negative 240. 5 times 80 is 400. That comes up to $160. So our largest profit, maximum profit, is right here. $650 when we produce 100 calculators and 100 scientific calculators and 170 graphing calculators. So the maximum profit is $650 when we produce 100 scientific and 170 graphing. That answer makes sense because if we're losing money on the scientific calculators, we want to produce the minimum, and we're making money on the graphing calculators, we want to produce the maximum of those, and that's what that point represents. That's the minimum scientific, maximum graphing. So that again was 2 variables, so we could do it on the graph. So if we get to 3 variables, how do we do it? Well, there are a couple of different algebraic methods that get used. All of them involve matrices. Now, matrix, if you're into programming, is basically, it's called an array in programming, where we put the numbers in and the location tells us something about it. And it's called the simple method we're going to use is called the simplex method, which literally is the simplest method that I know of to solve 3 variable linear programming problems. Now, there are a lot of textbooks that'll try to take a 3 variable or a 4 variable even linear programming problem and reduce it down to 2 variables so that you can graph with it. But it involves some pretty tricky algebra, and you have to be very careful because you can, even if you do the algebra correctly, you can combine some things that'll mess up your answer if you don't know what you're doing. So it's simpler to do a method like this where we're going to work with all of the variables rather than trying to get rid of some. Now in the simplex method, first of all, we must have a standard maximization linear programming problem. So what that means is 2 things. One, the objective function is to maximize. Well, that seems obvious if it's a maximization problem. The second is all constraints other than the trivial ones, which we'll talk about, must be less than or equal to a number. Some equation, some variables less than or equal to a number. Except x is greater than or equal to 0, y is greater than or equal to 0, z is greater than or equal to 0. However many variables we have, each variable is greater than or equal to 0. That's implied, even though those are greater than, those are implied. All other constraints must be less than or equal to. So, if we have a standard maximization problem, we can go ahead and proceed with the simplex method. So let's lay out a problem here that is standard or can be made standard. We're going to look at, that was only 2 variables. Let's get to a 3 variable example. Here we go. You have $12,000 to invest in a combination of 3 accounts. The first account is municipal bonds. I'll let this be X. It yields 7% return. The second account is bank CD. I'll let this be Y, which yields an 8% return. The third account is a high risk account, which I'll let be Z, which is going to yield a 12% return. To limit risk, we'll put no more than $2,000 in the high risk. That's in Z. For tax reasons, because there's tax breaks on interest on municipal bonds, we want at least 3 times as much in the bonds as in the CDs. So we want to maximize the interest for a year. So our objective function here, we're trying to maximize, and I'm going to use R for interest, for rate. 0.07x, that's the municipal bonds, plus 0.08y, that's the interest on the bank CD, plus 0.12z, that's the interest on the high risk account. We want to maximize that objective function. Our constraints, well, first of all, we have that Z, now it's implied, by the way, that X, Y, and Z after greater than or equal to 0. So we don't need to state those. We can't put a negative amount in any account. Stated that Z has to be less than or equal to $2,000. We can't put more than $2,000 in the high risk account. It stated that X needs to be greater than or equal to 3Y. We're going to adjust this equation in just a little bit. And we know X plus Y plus Z is less than or equal to $12,000. We don't have to invest it all, but we're not going to get anything out of it if we don't invest it. Back to this equation here. First thing, to use this equation in linear programming in a simplex method, we have to have all the variables on the left side of the equation, on the inequality. So I'm going to do that. I have x is greater than or equal to 3y. I'm going to subtract 3y from both sides. So x minus 3y is greater than or equal to 0. The next issue here, we see these constraints are both less than or equal to. This one is currently greater than or equal to. We can't have that. So what we're going to do to fix that is we're going to multiply this whole equation by -1. When we multiply an equation by a negative number, remember it flips the inequality. So -1 times x makes that negative x. -1 times -3y makes that a positive 3y. It flips the inequality to be less than or equal to, and -1 times 0 is still 0. So this inequality here is now negative x plus 3y is less than or equal to 0. Those are our constraints. So I'm going to write those constraints using something called a slack variable. What a slack variable is, the definition of an inequality, A is less than B, means that A plus some positive number C equals B. So I can turn an inequality into an equation by adding that slack variable. That's what C is a slack variable. It picks up, it's the difference between the two quantities, and if I add it to the one that's supposed to be smaller, then the two become equal. So it changes all of these inequalities into equations. So the first one here, Z is less than or equal to 2,000. I'm going to write that as Z plus, my first slack variable is going to be S, equals 2,000. Now I'm spacing this out for a reason. We won't do that yet. We'll do the spacing later. Z plus S equals 2,000. The next inequality here, negative x plus 3y. We'll keep them close together again. Now we have to have a different slack variable here because the difference might be different. So I'm just going to use t equals 0. And then of course we have x plus y plus z. We'll use a different slack variable. So we use u. That's going to have to equal 2,000 or 12,000 now. So we use this to create our initial tableau. A tableau is a matrix-like structure that we're going to actually use matrix operations on it, matrix row operations. But it has labels in it. Rather than just the numbers being arranged in the matrix, we actually have labels added to it that go with the column. So it's really not quite a matrix. That's why it's called a tableau. The first line of our tableau, well, first of all, we have to have columns labeled. We're going to start out with our variables, x, y, and z. And then we have our slack variables, s, t, and u. I'm going to leave a little space. We're going to add one there in a little bit. So for the first inequality or equation, I guess now, there is 0 for x, 0 for y, because there's no x or y variable. The coefficient on z is 1. Coefficient on s is 1. For t it's 0 and for y it's 0, and that equals 2,000. For the second equation here, the coefficient on x is -1, y is 3. There's no z, so that's 0. There's no s, so that's 0. Coefficient on 2 is 1. There's no u, so that's 0. And it equals 0. And for the last constraint, there's coefficient of 1 on x, coefficient of 1 on y, 1 for z, no s and no t, and there's a 1 for u, and that equals 12,000. Now I left a gap there because we're going to put a line across here, and below the line, we're going to put our objective function. But the objective function has to be solved. We have to change it so that the right side of the function is 0. So that means we're going to just subtract all of these and put them on the left side. Our last column here is going to be labeled R. So it's going to be a negative 0.07 is the coefficient for X. Negative 0.08 is the coefficient for Y. Negative 0.12 is the coefficient for Z. There is no S, T, or U, and there is an R, and that equals 0. Now, there was no R in any of these constraints, so we put zeros in for those as well. Now, many textbooks just use this as our tableau, with the labels up top as they are. And you know what the rows represent because of the numbers. Now, since they're beginning, if you're experienced using linear programming, you would be able to look at this table and see which variable each row stood for. But since we're beginning here, we're going to label them. And we label them by what's called the active variable, the variable that we know is greater than or equal to 0. And here, for these top ones, it's the slack variables. We know that if it's less than or equal to, each of those slack variables has to be greater than or equal to 0. It has to be positive. So I'm going to label this one, the slack variable we used there was S. Didn't mean to highlight that. The second row, the slack variable you used there was T. The third row, we used U. And in this bottom row here, I'm just going to label that R because that was our objective function. So that's the R row, the U row, the T row, the S row. Once we have that initial tableau, we have to choose a pivot. A pivot is a number we're going to use to clear out the rest of the numbers in that column. It's kind of like the addition or elimination method for systems of equations. What we did up above to find where those equations intersect, we multiplied one by -2 and then added them together, and one of the variables canceled out. That's kind of what this is like. So to find our pivot, we first find the pivot column. In the column is the column of the largest negative number. So the most negative number in the bottom row. So in the bottom row, the largest negative number is the negative 0.12. So that column is where our pivot's located. To find the row of our pivot, we use the smallest test ratio. Now, I should say if there were more than one number in the bottom row that was the same size negative, that were tied for the largest negative number, we would just pick one. It doesn't matter which one we pick. I usually just pick the one furthest to the right to stay organized. Same here. If in this column there's more than one number that has the same test ratio, that for the smallest test ratio, we can just pick one. The reason we do these steps is it avoids giving negative numbers where we can't have negative numbers. Remember, X, Y, and Z all have to be greater than or equal to 0. It's going to avoid pushing them into that negative region, which we can't do. So our test ratio is found by taking the number in this right-hand column divided by the number in our pivot column. 2,000 divided by 1 gives us a test ratio of 2,000. 0 divided by 0, we can't do that. So that cannot be our pivot. And I should say that this has to be a positive. Actually, it doesn't have to be positive. This has to be a non-negative number. So this test ratio has to be greater than or equal to 0. But that one's not possible because we can't divide by 0. The next one, 12,000 divided by 1 is 12,000. So the smallest test ratio there is obviously the 2,000 up here. So our pivot is going to be the 1. So we're going to use that 1 to eliminate all of the other numbers in that column. The other thing we're going to do is we're going to change the label of this row. That we take the label of the column that we pivoted on, and we put that where in place of the label for the row. Now the column labels up top here will never change. That's always going to be X, Y, Z, S, T, U, R. It's the row labels that are changed. That Z is going to replace the S in our next tableau, so it's going to become an active variable. It'll now have a value other than 0. So let's create our new tableau. In this new tableau, I'll just do the labels here. We got X, Y, Z, S, T, U, and R. The top row is the pivot row. None of the numbers in that row will change. All that's going to change is this label. So that's going to become a Z. So it's going to be labeled Z. This will be 0, 0, 1, 1, 0, 0, 0, 2000. That row is not changed. Now we need to clear all the other entries in that column. Well, this entry is already 0. That row does not need to change because that entry is already clear. So T, the T row, is going to be -1, 3, 0, 0, 0, 0, 0, 0. Sorry, I have to have the 1 in the T. I forgot my 1 in the T for my slack variable. Now for the U row, we're going to have to do some changes there. If I look up here, now I always start out with the row I'm trying to clear. So the row I'm trying to clear here is the U row. So I'm going to just do the U row. I'm going to subtract the S row. 1 minus 1 is 0. Now, if those values were different, I'd have to multiply each of them by different numbers to make them add up to 0. Well, I'm going to do U minus S. So 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. So I have 1, 1, and 0. 0 minus 1 is a -1 for S. 0 minus 0 is 0. 1 minus 0 is 1. And 0 minus 0 is 0. So 0, 1, and 0. 12,000 here minus my 2,000 is 10,000. So that value does change. Now we also have to clear the value in the R row for that column. This is going to be a bit trickier because what we're working with here is we're working with a -0.12 and a +1. To get them to cancel, let's see, if I do 25 times the -0.12, that gives me 3, or -3, and I add 3 times the 1, that'll give me a +3. That adds up to 0. So it's 25 times the entry in the R row plus 3 times the entry in the S row. So here I've got 25 times -0.07 is a -1.75 plus 0. That's a -1.75. 25 plus -0.08 is a -2 plus 3 times 0 is still 0. So that's a -2. This one better come out to be 0 because that's why we picked the values. 25 times -0.12 is a -3 plus 3 times 1 is +3, so that's 0. That's what we're trying to do, is 0 that out. 25 times 0 is 0 plus 3 times 1 is 3. So this becomes 3. Oops, what happened there? Oops, I hate my... There we go. Sorry. So this becomes 3. 25 times 0 plus 3 times 0 is 0. 25 times 0 plus 3 times 0 is 0. 25 times 1 is 25 plus 3 times 0 is still 25. So 0, 0, 25. Now I've got 25 times 0 is 0 plus 3 times 2,000 is 6,000. So this becomes 6,000 down here now. So this is my new tableau. Notice the big change is that this is no longer the S row, it's the Z row. The row Z. Z row sounds a little awkward. It's row Z. Now I have to repeat the process. As long as there's negative numbers in this bottom row, I have to keep going. I know I am done when that bottom row is all positive. So once again, I pick the largest negative number in the bottom row. That'll be the -2. So I'm going to look at that column. For test ratios, well, 2,000 divided by 0, that can't be done. Can't divide by 0, so that one's no good. 0 divided by 3 is 0. That's pretty small. That's 0. So I have a test ratio of 0 there. 10,000 divided by 1 is 10,000. So I'm obviously going to be using the 3 as my pivot. 0 is my smallest test ratio. So that means that this y is going to go over here and replace t as the row label in my next tableau. And I have to use that 3 to clear all the other values in that column. So in my new tableau, to clear my 0 on the row Z on top, this is already a 0. So that row is clear. So that row does not need to change. So this is 0, 0, 1, 1, 0, 0, 0, 2,000. Now my next row becomes the Y row now, row Y. And since that's my pivot row, it does not, the numbers do not change. The only thing that changes is that label at the beginning of the row. Row U there has to change. I need to clear it using the 3. If I did 3 times row U minus row T, 3 times 1 would be 3, minus 3 is 0. That'll clear that row. So 3 times 1 is 3, minus a -1 is 4. So this will be a 4. This is row U yet. Here I have 3 times 1 is 3, minus 3 is 0. That's what we wanted there. I have to have 0 in that column. Next we have 3 times 0 minus 0 is just 0. 3 times -1 minus 0 is just -3. 3 times 0 minus 1 is a -1. 3 times 1 minus 0 is just 3. Now that next column is going to be 0, so 3 times 0 minus 0 is just 0. This is what's going to change the most. 3 times 10,000 is 30,000, minus 0 is going to be just 30,000. Next, we have the bottom row that we need to clear. That's going to stay row R. Let's see. It looks like we're going to have to do 3 times R. That would make this a -6 plus 2 times row T. 2 times 3 make it a +6. That adds to 0. So 3 times a -1.75 is a -5.25. Plus 2 times -1 is -2, adds up to a -7.25. This better cancel out here. 3 times -2 is -6. 2 times 3 is +6. That adds to 0, which is what we were shooting for. 3 times 0 plus 2 times 0 is 0. 3 times 3 is 9, plus 2 times 0 stays 9. 3 times 0 plus 2 times 1 is just 2. 3 times 0 plus 2 times 0 stays 0. 3 times 25 plus 2 times 0 is going to be 75. And again, here's our big change in the last one here. 3 times 6 is 18, plus 2 times 0 is just going to be 18. So 18,000. So there's our next tableau. Notice again that this is no longer the T row, row T, it is the row Y. However, there's still negative value in the bottom row, so we are not done yet. That is the only negative value in the bottom row, so this is going to be our pivot column. Our test ratios, well, 2,000 divided by 0 can't be done. That's a 0. That's impossible. 0 divided by -1, well, that would be, we can't divide by a negative. We don't want to use a negative value as our pivot. So that one's out. 3,000, well, that's the only one that's left is the 4, so we're going to pivot around the 4. So now of course, the X is going to become the label for that row. That's going to be, the U row is going to become the X row. So let's set up our new tableau. X, Y, Z, S, T, U, R. We need to clear the rows. Well, in row Z, this is already a 0, so that's already clear. So row Z does not need to change. Row Y. I'm going to get rid of that Y. The highlighting there is not serving any purpose anymore. Row Y is a -1. So to clear that, it's going to be 5 times row Y plus row U. Or sorry, 4 times row Y plus row U. 4 times -1 is -4. Plus 4 is 0. So that one is cleared, but we got to do everything else in the row. 4 times 3 is 12, plus 0 is just going to be 12. Four times 0 plus 0 is still 0. Four times 0 plus -3 is going to be just -3. 4 times 1 is 4, plus -1 is 3. 4 times 0 is 0, plus 3 is 3. 4 times 0 is plus 0 is still 0. Now 4 times 0 is 0, plus 30,000 is 30,000. Row U is our pivot row, so the numbers don't change, but we're going to change the label to X. Let's say 4, 0, 0, -3, -1, 3, 0, and the 30,000. And now we have to look at row R. In row R, we need to combine -7.25 with 4 in some combination that'll make it 0. Let's see. If I do 16, 4 ain't going to do it. I have to do 16. We'll do 16 times R. That'll make that a negative. What does it make it? 16 times a -7.25. That'll make it a -116. So that'll work, yep. Plus 29 times row U. This number's going to get large, but it's what we have to do. So again, 16 times a -7.25 is 116. 29, or -116. 29 times 4 is a +116. So that adds up to 0. Which is what we had to do there. Well, 16 times 0 is 0, plus 29 times 0 is also 0. 16 times 0 is 0, plus 29 times 0 is still 0. 16 times 9 plus 29 times 3, that adds up to 57. 16 times 2 is 32, plus 29 times 1 is a -29, that adds up to 3. 16 times 0 is 0, plus 29 times 3 is 57. 16 times 75 is 1,200 plus 29 times 0. That's just going to say 1,200. Here's the big one. 16 times 18,000 plus 29 times 30,000. What is that? That becomes 1,158,000. Now, every number in this bottom row is positive. That means we're done. We can read our answers off. First of all, the maximum. Oops, come on. Of our objective function can be found taking this value divided by the value in the R column. 1,158,000 divided by 1,200. Oh, what's that come out to be? $965. So $965 in interest is the maximum interest. The value for X, this is row X, so that's the row that we would find the solution for X in. We take the number in this last column, excuse me, divided by the number in the X column. So 30,000 divided by 4, which is 7,500. X, remember, was municipal bonds, so we're going to invest 7,500 in municipal bonds. For Y, it's the value in the last column, 30,000, divided by the value in the Y column. So 30,000 divided by 12 is $2,500. We had to have at least 3 times as much in bonds as we did in CDs. 7,500 is exactly 3 times 2,500. And Z, this is the row Z. We have 2,000 divided by 1 in the Z column is $2,000. So we would earn our maximum interest of $965 when we put 7,500 into bonds, 2,500 into the bank CD, and 2,000 into the high risk. Whew. Okay, there's a mouthful there. And I realize there's a lot of stuff going on there that you've probably never seen before. If you're confused at this point, don't worry, you're not alone. And unfortunately, we only have time for the one example because it takes like 20 minutes per example. But this is a standard maximization problem. Now, the next step what we've done so far is, well, let's do the next step. The next step would be to look at 2 things. The first thing we would look at is minimization problems. To fix that, let's say we have an example here where we're asked to minimize C equals 2x plus 5y. We can change it to a maximization problem. By multiplying by a -1. So this problem would become maximize. And my pen's not functioning real well here. Maximize, and we're going to change it from a C to a P. We would take this equation times -1. That'd be -2x minus 5y. Since this is the negative, maximizing this function would be the same as minimizing this one. the values we get for x and y will be the same values that minimize that other function. So that would fix the having a minimization problem rather than maximization problem. We just convert it to a maximization problem. As long as all the constraints are still less than or equal to, we're good. The second problem we have, or we could have, would be sum of the constraints. Are an equation of some sort is greater than or equal to a number rather than less than or equal to. Now, we are allowed to do what I did in that last example. We can just multiply it by a -1. That's allowed, but sometimes that can give us some extraneous solutions. So there is a safer method that the book goes over in section 5.4. And what it is rather than using a slack variable, they use a surplus variable. Now, unfortunately, this brings in some other issues that have to be fixed. You know, if A is greater than B, that implies that A minus some positive number C equals B. But this gives us some negative values in our solution. Remember, part of the condition of a standardized problem is X, Y, Z, all of the variables have to be greater than or equal to 0. That slack variable would not be in that point. We would be subtracting it. So it violates some of the basic functions or fundamental requirements of a problem. So we have to fix that in our first steps. Once we create our initial tableau, we must first address that negative value to give us an acceptable answer. Basically what it gets us outside of the feasible region. So we have to do some things to get us back inside the feasible region with our tableau. Now, with that all said, I want to make some comments on this unit. Like I said, this unit used to be 2 weeks long, but when the course had to be shortened to 12 weeks, we squeezed it into 1 week. And it's more material than you can really expect to do in 1 week. So there are really 3 levels of this week's material. Level 1 is the 2-variable LP problems that we solve by graphing. And then also level 1 is the basic simplex method. For standard maximization problems. This is sections 5.1 through 5.3. I hope that all of you can get those pieces. I realize the example of the simplex method we did tonight is complex. A lot of steps happened. You didn't have time to absorb it all. But hopefully using the examples in the book and the other examples in the video lectures, we can get you there. Level 2 is the non-standard maximization problems, which is where the constraints are greater than or equal to. And of course, the minimize, which we have to change into a maximization problems. This is section 5.4. Now, I expect you to struggle a little bit with the level 1 stuff. This is the part where people really start to struggle. Historically, when I've taught this course, only about half the class really caught on to this section. Now, I'm not trying to discourage you, but I'm letting you know that so that to avoid frustration. If you're struggling with it, I assure you that half the class or more is also struggling with it. And then the third level, level 3, is something called dual problems, where we have to convert a maximization problem into a minimization problem in order to complete it, or the other way around. This is, of course, section 5.5. And I hate to say this, but the times I've taught this course in the past, I've only had maybe 2 or 3 people in each section that really get this material. Again, I'm not trying to discourage you. I'm not trying to say you're not going to get it. I'm just saying if you don't get it, don't get frustrated, don't get down on yourself. This is pretty tough material. To really have a fair shot at getting, oh, my pen is not switching for me, to getting these 2 pieces, we would really have more time. So what I've done to compensate, I've done 2 things. One is for the week 11 quiz 11, I reduced that requirement of 80% on the homework. You now only need 50% on the homework in order to have a shot at doing the quiz. Like I said, I've had too many students that just could not get to that 80% and emailed me to get into the quiz, or didn't email me and just didn't take the quiz. I want you to get as many points as you can out of this week. So get up to at least 50% and then get what points you can out of the quiz. The other thing is next week, meet session is not required. It's optional. So you won't lose anything if you're not there. But I will give extra credit for attending the meet session, 8 points, just like a standard meet session. And what we will do in that session is we are going to go over, and really what I'm going to do is I'm going to take a poll at the beginning of the meet session and see what students prefer. We'll go over sections 5.4 and 5.5 if that's what you wish, or we'll do a little bit of review for the test. Now I see a couple of comments here in the chat room. Let me get back to it. Send me an email, Dominic, because by the time I get a chance to get back to WebAssign, I'll forget that you asked about that. Send me an email and I'll make sure I go in there and get that changed for you. Other questions. Is there a good amount of this module on the final? That's a good question. I looked at it, but I don't remember what I saw. Actually, I can check right now, maybe. It looks like they have 1 question. Oh, nope, they don't. So no, they do not ask anything about, well, they do. They don't use the section here. They're using the review. So there are at least 4, actually, it appears to be, linear programming questions on the final, which is a little less than the other sections. And at least 3 of them can be done with the lesser the level 1 material. There's actually 3 out of the 4 can be done with the level 1 material. There's only 1 of them that would require that level 2 or level 3 stuff that we were mentioning. So it's not quite so bad. In the quiz for this week, there are a couple from each of those more difficult sections. So just so you're aware of that. Okay, with that, I'm going to turn off the recording. Anybody have any questions?